Hello, welcome to the concluding part of our lesson on moment distribution method of structural analysis. My name is Engineer Dr. Edidiongi Ambrose from the Department of Civil Engineering, Akwa Ibom State University. So in this part, we will be looking at beam with support settlement. So all the cases that we have been looking at, the continuous beam that we have been considering so far, it has been assumed that the support remain rigid. That means there is no settlement. However, when there is differential settlement between two or more supports of a beam, there will be a relative vertical movement between those supports, and this will induce bending moment and shear forces in addition to those generated by the load. So what that means is that if you have a support settles, if all the supports settle at the same level, no problem, but in practice, they don't always happen. Usually, one support will settle more than the other, and that introduces what we call differential settlement. And because of that differential settlement, there is an induced moment, induced shear force, in addition to the general one that is caused by the loading of the structure. And so, this is a case that we are going to consider here. And so if you have, these are the loading condition, the common, you have already done the fixed end moment due to load. Now these are the fixed end moment induced due to support differential settlement. So if we have delta as a relative settlement between two supports in a beam, and the span of the beam is L, and the flexural rigidity of the beam is EI, that where E is modulus of elasticity and I is moment of inertia. So the fixed end moment due to support settlement, it can be calculated using the formula in this table. And note that this fixed end moment, once they are calculated, they will be added to the fixed end moment in those span caused by the loading. So in any way, case when there is support settlement, you will have the fixed end moment of the load plus the fixed end moment due to support settlement. And so if you have a beam, like in this first case, this is a beam AB. If support B settles by an amount delta, that is the right hand support, this will be the fixed end moment due to support settlement. At the left support and at the right support, they will be the same at the left support and at the right support. Now, if it is the right support that is settling, that is in this case support A settles by amount delta. So this will be the fixed end moment at both ends of the beam due to support settlement. You can notice that if the right hand settles, it is negative. If the left hand settles, it is positive. Take note of that. You will need them as we proceed. So we are going to continue by solving this example 5. Example 5 says calculate the support moment for the continuous beam below, assuming that support B settles by 12 mm. You have to take EI as 24 times 10 raised to power 3 kilonewton meter square. So this is the beam, the continuous beam. It is fixed at A and simply supported at ND. But the major thing is that support B here settles by what? By 12 millimeters. So let's go ahead and solve this, and I can tell you it is very simple, just like what we have been doing before. Just one little addition. So as usual, we calculate the stiffness factor. If we go to beam AB is fixed at A, continuous at B, so it's considered to be fixed. So that's why you say the stiffness factor is 4AI over L, which gives us this. Beam BC, B to C is continuous at both ends, so it's considered to be fixed. So it is 4EI over L. That gives us this. But beam CD, continuous at this near end, simply supported at the far end. So it is 3EI over L, which gives us this. So we go to calculate the stiffness factor at support A. because there is only one member meeting there, and at support D, the distribution factor for those two supports are what? 1. But at support B and support C, we can now go ahead and calculate the distribution factor. For instance, at support B, there are two members meeting there, member AB and member BC. So for this B going to A, for B going to A is a stiffness factor of A, which is a stiffness factor of AB. That is the stiffness factor of AB divided by the sum of the stiffness factors of all the members meeting at that joint, which in that case is a stiffness factor of AB plus the stiffness factor of BC. So that gives us this. And if you do for B going to C, it will be the stiffness factor of BC divided by the sum of the stiffness factor of AB and BC, which is this. And it gives us this. So if you do the same way, you can have the stiffness factor for DCB and for DCB and DCD as shown. So this need to be connected. This actually should be DCD. Distribution factor for CD. That will be corrected. So now let's go to the fixed end moment where the main difference will be. So if you go to fixed end moment, remember this is the beam and it is support B that is settling. So this support settles and it settles by 12 millimeter, in which if you convert it to meter, that is dividing by 1000, it will be 0.012 meter. Remember that EI is taken as 24 times 10 raised to power 3 kilonewton meter squared. So if we go to fixed end moment at AB, remember it is B that is settling. So if it is B that is settling, that is the right hand support settling. That means the effect due to, the fixed end moment due to induced by the support settlement is going to be negative both at A and B. We can go back to see the table. Remember this table. If it is the right hand support that is settling, the fixed end moment due to induced support settlement is negative. So let's go back. If we go back there, that is why originally for this fixed end moment at AB, the one due to load is minus WL squared over 12. We know that. So that is why we have this minus WL squared over 12. But the one due to the settlement of support B is minus E6 EI delta over L squared. So we now put in the value. This is WL squared over 12 and this is 6 EI delta over L squared. So when we calculate that, it gives us this value minus 123 kilonewton meter. So this is a fixed end moment at A going to B due to the load and due to the settlement of support B. Now fixed end moment of B going to A, this is it. Originally due to load, this place will be positive, so it will be positive WL squared over 12. But because of the settlement of B, the fixed end moment due to settlement is this minus 6 EI delta over L squared. So if you put your value, you have this is L squared over 12, and this is 6 EI delta over L squared. And so note that in this case, this one is positive, WL squared is positive, but 6 EI delta over L squared is negative. So you have this positive minus this. That's why we have this 27 kilonewton meter as the fixed end moment. So we go to BC. By the time you move to BC, notice that support B is the one settling it down, which is now the left support. When we expand AB, it was the right support, and the value of fixed end moment for the settlement was negative. But when we have support BC, it becomes the left support, and so the value of the fixed end moment due to support settlement will now be positive. Let's again go back and confirm that. Remember this table, if it is the left support that is settling, the 6 EI I delta over L squared will be positive for both sides. So take note of that. So that is why if we go to fixed end moment for BC, that's this place B going to C. The load in there is point load at midspan, which the fixed end moment is what? PL over 8. But because it is a left support, it is minus PL over 8. Now the fixed end moment due to the support settlement here is plus 6EI delta over L squared. So by the time we put the value for all of those ones, this is what we have. This is PL over 8 and this is 6EI delta over L squared. So that gives us this. Remember, PL over 8 is minus, this one is plus, so that gives us this. The next one is a fixed end moment for support C going to be, when we are here, remember it's the support B that is settling, so the fixed end moment due to support settlement is positive. But at this point, remember the fixed end moment here due to load will be plus PL over 8. So that's why we have this PL over 8 plus 6EI delta over L squared, which is the one induced by the support settlement. So when we put the value, this PL over 8 and this is 6EI delta over L squared. So that gives us a fixed end moment of 102 kilonewton meter. Now when we go to support C, remember it was support B that settled. So when we go to span CD is not affected in any way by the settlement in support B. So the fixed end moment at span CD will still be the way it was in previous cases, because the settlement here is the support B that is settling. So it will affect only span AB and span BC. So we can now go here and do our fixed end moment, which in this support C, it will be minus WL squared over 12. In this case, W is 30 and L is 7. While at the right hand side, it will be plus WL squared over 12. So that is why you will have this. So having done this, we have been able to compute our fixed end moment. So the rest is just the same thing that we have been doing. So we now go here. This is our correcting distribution factor that we calculated in this first row. The second row, we now put our fixed end moment that we have calculated. So when we finish, we now note that support A is fixed. So if support A is fixed, it means you can't take a distribute load from that support, but you can distribute load towards that support. Also take note that support D, which is an end support, is simply supported. But that means we need to keep the load at the moment at this support at 0. So because the fixed end moment is already 122.5, so for us to make it 0, to balance it, we introduce a moment of that same magnitude but equal in sign. This was a clockwise moment, so we introduce an anti-clockwise moment of the same magnitude, such that when we do 122.5 minus 122.5, we have 0. And once we do that, we don't move. We don't carry over any moment to that support. So the next level is just for us to distribute as we have. So you come here, what's the difference between this and this is going to be negative. We find the positive of that difference and distribute it to this based on their distribution factor. And we do the same. So when we finish, we now sum. So when they sum all the moments here, you have 122.96. You have this one 26.9 minus 26.9, 146.15 minus 146.15, and this place 0. So this is how, by doing that, you have distributed the moment, and this is the final support moment. So with this, you can go ahead and draw the bending moment diagram by drawing the support moment diagram and drawing the simply supported moment diagram, superimposing one on the other. And so you have the bending moment of this continuous beam. And the next thing, you can now go ahead and calculate the support reactions and then draw the shear force diagram. So with this, we have come to the end of our lesson. on moment distribution. So just a quick one, you can do these exercises. It say using the method of moment distribution, determine the support moment and draw the bending moment and shear force diagram of the continuous beams below. So for case 1, you have this. You notice that in this case, the beam it has an over a cantilever at the left, this left support, while this side is simply supported. And for this case, it's fixed here, it has a cantilever here. For this number 3, fixed here but simply supported. Please take note of that case. Then exercise 4 is using the method of moment distribution, calculate the support moments and then draw the bending moment and shear force diagram of the beam below. Assuming support C settles by 10 mm, take EI as 25 times 10 raised to power 3. So you just do that, taking note that support C is settled by what? By 10 millimeters. So thank you very much for watching the video to the end. Please don't forget to like the page. So subscribe or like this video and subscribe to the page so that you can be getting our subsequent video. Thank you very much.